So this part of our course marks a transition, very important transition. Up until now, we have been talking about particles or objects moving, right? We're now going to move away from that type of motion, linear motion, circular motion, and we're going to start talking about something else that is the other cornerstone on which modern physics is based. We've been talking about mechanics up until now. Now we're going to talk about vibrations and waves. And a little later, I'm going to do some demonstrations next week, which will show you how different they are. You may have heard that light is a wave, right? But light is also a particle. And so how can it be both at the same time? Well, the reason is that our human models of how things work are based off what we can see. And if we can use those models to predict behavior, we say that they're a good model. So we take Newtonian mechanics, for example, and can use it to predict the motion of the planets, but also the motion of a bug in the air. Right? Very large differences. If we want to get down to the subatomic level, or even the atomic level, and we want to look at things like electrons, the only real way to look at electrons in an atom is using waves and our understanding of waves. So this is sort of an exciting thing that we're going to do. But again, I'm going to start very simply, and we're going to build it. I'm going to show you where the equations come from that we're going to use. You're not going to have to derive these equations, so I would prefer, unless you're taking Cornell notes, that what you do is listen. Okay? All right, so here we go. Vibrations and waves. The topics are simple harmonic motion, energy in the simple harmonic oscillator, the period and sinusoidal nature of simple harmonic motion, and then we'll go on to other topics later on. Okay, so this part of the unit is about simple harmonic motion, also known as SHM. And what we do with simple harmonic motion is we're looking at a repetitive motion or a periodic motion. So if an object vibrates back and forth, like this one, let me show you. Right? Notice how that's moving backwards and forwards. This is actually a model for what's up there. In this picture, the spring can be both compressed and there's a force, and it can be extended and there's a force. This, or these springs, the only springs I have were extension type springs, right? Can't compress them. So what I did was I put one on each side. What that does to the effective spring constant is double it. No, halves it. Sorry, halves the effective spring constant because they're in series. It's double the length. I mean, it's basically two. You can probably go about deriving it yourself, but if you put two springs in parallel, you've doubled the spring constant. That makes sense, right? Well, from personal experience, you can try it out. Okay. All right. you put two springs in parallel, you double the spring constant. Have you ever been to Six Flags and seen that thing where they basically zip people up in the air, right? You look on the side, what's there are two huge banks of springs in parallel, which they compress, right, before they start, right? One individual spring is not going to be enough to launch those people in the air. Actually, that's my favorite ride at Six Flags. Unfortunately, no Six Flags this year. Okay, so you've seen that. Now let's get back to this. So this mass and spring system is a useful model for a periodic system. Periodic means an object oscillating back and forth over the same path, each cycle taking the same amount of time. A cycle is one complete back and forth motion, right? Just a little tip here, if you're looking at back and forth motions, always start at either one extreme or the other. Do not start in the middle because you can make mistakes when you count, right? But it's very clear when something comes, if it starts here and comes back to here, that's one cycle. So any vibrating system where the restoring force in this case is this force operated by the spring, is directly proportional to the negative of the displacement. It is in simple, so it's in simple harmonic motion and is often called a simple harmonic oscillator because it oscillates, right? SHO. So we assume that this surface is frictionless. Our model here on the bench is not frictionless, so it eventually stops, right? It eventually stops. And where it stops, this position we designate as the origin or equilibrium point, right? The place where it would stop. Now, we can pull it out like this, and you'll notice that it goes to one extreme and another. Those extremes are each called the amplitude. One is negative, one is positive because of the displacement. The displacement is either positive or negative. Now, according to Hooke's law, the force of a spring is equal to the negative of the spring constant times the displacement, right? Minus kx. You remember that? Yeah. Okay. So if we push a spring to the negative direction, it's going to have a restoring force, which is the negative of that, right? Its restoring force is going to be back to the positive. If we extend the spring, the restoring force is going to be back the other way. So that's what I just said. The point where the spring is neither stretched nor compressed is the equilibrium position, and we measure displacement from that point. The force exerted by the spring depends on the displacement. Remember, if we look at a force versus displacement graph, right, you did this in one of your labs. What you see, or what you will see on the data, is something that looks like that. The force is changing. Can you see that shape?
Yep.
Okay. The slope of this line we call the spring constant, right? And the amount of work done depends on where we start and where we end is equal to the area under that graph, right? So where you start is very important. If you start up here, the amount of work done is different, right? Even if the displacement is the same. That is the force, and that is in fact part of the definition of a simple harmonic oscillator, right? A simple harmonic motion is that you have to have a restoring force which is proportional to the negative of the displacement. So if we start off with Hooke's law, right? We know that the force is not constant. So the acceleration is not constant either, which means we cannot use kinematics. Who just joined? Okay. We cannot use kinematics. So let's have a look. Displacement is measured from the equilibrium point, x equals 0. Amplitude is the maximum displacement. Who knows what, on a radio station, what the letters AM mean?
Amplitude.
Amplitude, what?
Measure.
Modulation. Modulation means to change, right? So in an AM radio station, what they do is they put the signal, the audio signal, on top of a radio wave, and it's encoded by changing the amplitude of the radio wave.
Crazy.
Right? And then at the other end, the radio wave is removed, leaving just the audio section. And that audio section is then amplified so you can hear it. Maybe you'll understand that next year if you're doing AP. Pretty cool. It's very cool stuff, actually. A cycle is a to and fro motion, and this cycle shows a full to and fro motion. Period is the time required to complete one cycle. Time is what? In what units? Seconds, right. Frequency, on the other hand, is the number of cycles completed per second. Based on these words in D and E, who can tell me what the relationship is between period and frequency? The mathematical relationship between period and frequency. Yes, Spencer. They're inversely proportional. Very good. And you were able to determine that because okay, so what you're saying is that this is seconds and this is per second. Right, that's absolutely correct. And in fact, we usually write this like this. The letter for period is a capital T. That's sort of confusing because when you get to thermodynamics, capital T is temperature. But we start running out of letters in physics, even with the Greek alphabet. And the letter we use for frequency is when we're talking about mechanical vibrations. When we're talking about light, we use the letter nu, N-U, right? So lowercase Greek letter for N, yes.
Can you repeat that? You said you used nu for
Light,
light. Okay.
frequency of light. Okay, lowercase f you use for mechanical vibrations, at least in this textbook. It's not always the case. So the units here are seconds, or if you need help, you can put seconds per cycle, but a cycle is just a number, right? And this one is cycles per second, or seconds to the -1. Seconds to the -1 is given the SI unit hertz. You know, you've heard the word hertz, or you've seen it written on your electronic devices, right? You're going abroad, many places have 50 cycles per second line power. You want to know if you can use your electronics or electrical devices abroad. Either it has to stay 50/60 hertz, or there has to be a switch which allows you to switch it. That includes hair dryers. Okay. Well, with hair dryers, so long as you have the voltage change, that's okay. With some things, if you don't have that, you could blow up your electronics. Okay, if the spring is hung vertically, the only change is the change in the equilibrium position. We have moved the thing from oscillating in this region of the spring to this region of the spring, right? There's more force now, because we added a mass and moved the equilibrium position. The equilibrium position would be in the middle of this in both cases. Yeah.
Could you say, I don't know, but let's say amplitude is the difference between those two equilibrium points, or would that be wrong?
No, you're right. I mean, they're equal and opposite. The amplitudes are equal and opposite. They're the positive amplitude, the negative amplitude, and they're both the same magnitude.
So like how much you pull it down, basically.
It's how much you pull it down or how much you push it up if it's a compression spring also. That will be your starting amplitude. All right. So in this case, what's happened is the force of gravity has pulled down the mass, and there's a new equilibrium position. So we already know that the potential energy of a spring is given by this. US is 1/2 kx squared. You remember that, right? Spring potential energy. So the total mechanical energy is then going to be the kinetic energy plus the spring potential energy at any point in time. Right? At any point in this cycle, there's going to be spring potential energy and kinetic energy. Who can tell me what the energy is like at this position? Yeah?
Well, there's no kinetic energy and there's a lot of potential energy.
Right. So what would that equation change to?
I'm not sure.
All right, let me go back to the board so you can see.
Oh, it would just be just kinetic energy. Or just potential energy, so 1/2
kx squared,
yeah.
exactly. And notice that it doesn't matter whether the amplitude is positive or negative. This is always going to be positive because it's squared, right? Total mechanical energy will be conserved as we're assuming the system is frictionless. There are no external forces acting, all right? We always start that way. It's sort of, you look at what is the major thing that you need to figure out first, and then you start adding back all the things that modify it. So you start with a simple system and you make it more and more and more complex. So let's have a look at the energy. If the mass is at the limits of its motion, which are A and C, the energy is all potential. If the mass is at the equilibrium point, the energy is all kinetic. Where does the maximum velocity occur? Yes.
Equilibrium point.
At the equilibrium point. And that velocity can be either positive or negative depending where it is in the cycle. But that's where kinetic energy is at a maximum, because the velocity is a maximum. It's at the equilibrium point. And since we know what the potential energy is at the turning points, we can say this, that the total mechanical energy is equal to 1/2 Ka squared, where A represents the displacement of the amplitude. All right, so now we've got a fixed thing. 1/2 Ka squared is the total mechanical energy, which is conserved. So kinetic energy at the turning points is 0. Total mechanical energy of the system is therefore 1/2 mv squared plus 1/2 kx squared, right? Or 1/2 Ka squared equals 1/2 mv squared plus 1/2 kx squared, depending on where you are. And we'll call that equation 1.
Wait, why is it 1/2 Ka squared?
Well, because you just told us, right?
I thought it was just 1/2 Kx squared.
Right, but x at the turning points is equivalent to the amplitude, A, right?
Yeah.
So I changed it, right? So now total mechanical energy is 1/2 Ka squared. That's the maximum it can be. I know that this is difficult to keep track of,
Yeah.
all right? But I want you to, I want you to do what you just did. Ask me, where did you get that from, right? I know this is difficult, but I need to go through it once. And since I'm recording this, we can go through it, you can go through it again, right? So now we've got kinetic energy plus spring potential energy at any point along the path is going to be 1/2 Ka squared, because we know that's the maximum energy of the system. At equilibrium, where x equals 0, and the velocity is a maximum, we get 1/2 Kx squared is equal to 0, and that equation 1 simplifies to that. 1/2 V max squared equals 1/2 Ka squared. See what I'm doing? We're going to the extreme points to see what we can find. We can't use kinematics with this, because when we assume in kinematics that the acceleration is constant. And we know with a spring, it's not. The force changes depending on the displacement, which means the acceleration changes, right?
Yeah.
We can reorder this. We got V max squared equals K over MA squared, or V max is the amplitude times the square root of the spring constant divided by the mass. We rearrange equation 2 to get the spring constant in terms of V, M, and A, and that's called equation 3. And there's a reason I'm doing this, so just hang tight. So we can now derive an expression for the velocity at any time along the path in terms of displacement, the maximum velocity, and the amplitude. So from equation 3, we put K into here. Here. Right? We get rid of K. And so now it looks like this. 1/2 mv squared plus 1/2. Oh, I just saw that. Excuse me. Oh, no, that's right. That's right, because we're replacing K with an M. Yes. Was 1/2 M times V max squared over A squared, right? Times X squared equals 1/2 V max squared over A squared times A squared. And that simplifies to that. I take the terms in V max to the other side. And then I can bring out the V max squares to get this. Or the velocity is plus or minus V max times the square root of 1 minus X squared over A squared. I'm not expecting you to remember this. I'm expecting you to try to follow it, right, as I talk. All right, so now what I want you to do, people at home, it's going to be more difficult for you. I want you all to get in a position where you can clearly see this peg as it rotates. I mean, very clearly see it. If you have to move your seat, please move. All right, move over to that side, bring a stool with you, because you're going to have to get down at this level to do what we want for this experiment, right? You have to get down to eye level. Don't get in the way of that camera. Yeah. That's okay. You can go over there if you want. Over that, so you can all see. Spencer, can you really see both sides of that sitting there?
Yeah.
Really? So you can see it at that point?
Yeah.
All right. So what I'm going to do is ask you to cover one eye, right? And then I want you to get down at the level of this. And the reason I want you to cover one eye is to get rid of your three-dimensional perspective. Because what I'm going to ask you to do is think about the motion of this peg in 2 dimensions, right? Assume that there is a plane, right? Vertical plane, which you are trying to look at the motion of this. All right. What is the peg's motion doing? Let's pretend you don't know the peg is on a circular round table. If you know what it's doing, you can just put up your hand. Okay, so Peter, what do you think it's doing?
It speeds up in the middle and it slows down.
Right, and does it stop at the end?
Yeah.
It does. So what he's saying is that in the middle, if this is the middle of where it is, which would be the furthest point or the closest point to you, it's going the fastest. And at each edge, in your perspective, it stops and turns around. You see that? Yeah? It does that, yeah. Which is simple harmonic oscillation, or it seems to be. Like a pendulum, yeah. Everybody okay with that?
Mhm.
All right, so now back to your seats. And by the way, you'll find all of this in Giancoli if you want to read Giancoli. Most people do not want to read Giancoli. They want to use it for looking up examples of problems, which is actually one of the best ways of using it. most textbooks are not meant to be read. They're meant to be referred to help with your understanding. Now, some people can read a textbook and fully understand. Jerry Sung was one of those, which is a little frightening, actually. Okay, so by looking only at the motion in the x-axis, this is the x-axis that's defined here by this dotted line. Or if you want to look at the perspective of you down at eye level with the table, you can look at the thing that's shown in B. It appears, right? Emphasis on appears. It's because it's not actually doing this, right? It's just that if you were an ant in two-dimensional space, you wouldn't know the difference, right? It appears the object's oscillating backwards and forwards as shown in part B of the figure. Its speed at each extreme slows down to a stop before changing direction. And the speed at the midpoint is fastest. It has the appearance of simple harmonic motion. Why is this important? Well, I'll get to that in a second, but the first thing we're going to do is watch this. This is a simulation of what you just saw here, but for something moving up and down. Right, notice how going around in the circle, and its height, vertical height, is keeping track with the spring, right? Now we rotate it. You can still see it's moving in a circle, but it definitely looks much more like the motion of the spring now, right? Okay, so it's useful to see if we can make use of the mathematics of circular motion to help with the description of simple harmonic motion. Now, when I say circular motion, Jean Coley would assume that you've already done chapter 8. But depending on where we get to in a particular year, I will drop chapter 8 and move to chapter 11, because I think it's important for anyone who's not going on to AP physics to have done at least simple harmonic motion, because it gets into some of the properties of waves, which describe many of the things that you will see in nature. So examine the top part of the figure to the bottom right on this presentation. So we have two triangles here. We have this one here formed by V max, V, and this side here, where that's theta. And we have this triangle here, which has a length of A, the amplitude, right? Because when it's over here, that's the maximum point, maximum displacement. Over here, it's the maximum displacement. So that's A, the amplitude. This is X, and according to the Pythagorean theorem, this is going to be the square root of A squared minus X squared, right? Yeah. They're similar triangles. So the ratios of the two sides to the hypotenuse is going to be the same. So the equivalent sides for this triangle, if we look at the ratio of V divided by V max, are X and, sorry, A and the square root of A squared minus X squared. Right, those are the equivalent sides. We take the ratio, it should be the same because they're similar triangles. So we can write that down, right? There's the ratios. The velocity over V max is going to be equal to the square root of A squared minus X squared divided by A. Everybody happy with that? This would have done geometry, huh?
Mhm.
Well, we can put the a squares back inside, do that. And now what we've got is v is plus or minus v max times the square root of 1 minus x squared over a squared. Yes,
So you generated the same formula we use like for conservation of energy.
how about that? Equation 5 is the same as equation 4. Most people would not be able to see that because we've already gone past it, but I'm going to go back to equation 4. There it is there. Look at that. I'm going to quickly race through to equation 5. Right? So why did I go through all of that? To show you that we could use the math of circular motion to simple harmonic motion, okay? See how we do things in physics? It's sort of like, let's see, use what we know if we can, yes.
Oh, no,
Okay. So we can now determine the period of simple harmonic motion because it's equal to that of the revolving object on the turntable making one complete revolution, right? It's going all the way around, which is a distance, right? Divided by a time, which is the period, and that's going to be equal to the average velocity, average tangential velocity, right? Which is V max. Yeah. So tangential velocity, V max, is the distance traveled around the circular path, 2 pi times the amplitude, divided by the time taken, which is the period, t. So V max is equal to 2 pi amplitude over t, implies that t, the period, is equal to 2 pi a over V max, or the frequency, which is 1 over the period, is V max over 2 pi a, and we're going to call that equation 6. The ratio V max over A can be written in terms of the spring constant K and the mass M using equation 3. Here's equation 3, right, where we derived an expression for the spring constant. Now let's rearrange it. We've got K over M equals V max squared over A squared. Means V max over the amplitude is equal to the square root of K over M. If we substitute equation 7 into equation 6, that is, we're replacing a V max over A with the square root of K over M, we get that. Now I'd like you to take out your equation sheets. And I'd like you to look under the section for waves. You see it? You see that equation? Yeah. And we can, did I give you one for period as well on the equation sheet?
Oh, wait, you gave the period one, but not the frequency.
Oh, I gave the period one. Well, what's the period one going to be? It's going to be the inverse. What's the inverse of that? Right, 2 pi m root square root of m over k. Yeah.
Oh, I thought,
Huh?
yeah,
Which one is it? Which number?
under waves,
Uh,
so there's 7 and 13. Okay.
One of them will period, though.
Oh, yeah,
Well, I've got 2 equations for period.
No, one of them for a pendulum, one.
Oh, okay. Okay. Let's have a look at an example. When a 65 kilogram person climbs into a 1,000 kilogram car, the car's springs depress vertically by 2 centimeters. What will be the frequency of vibration when the car hits a bump? Ignore damping. What is damping? Damping is the equivalent of friction in a simple harmonic motion system. Obviously, it's no longer undergoing simple harmonic motion if there is damping, because now the restoring force is not equal to the negative of the, yes.
If you look at simple harmonic motion, the fact that you're saying it's simple, does that mean there's like another kind of motion?
Yeah, there's periodic motion, which is not so restrictive,
Okay.
right? So we make a definition of simple harmonic motion, which I gave you at the beginning of the presentation, all right? And if friction is in there, it doesn't meet that definition. But the majority of the motion is described by the simple harmonic motion, right? So mass of the person, 65 kilos, mass of the car, 1,000 kilos. The total mass, 1,065 kilos. The displacement of the car, 2 centimeters or 0.02 meters. The frequency is unknown. Is our car, is our person coming in and sitting on top of the car in this case? That's the displacement. Frequency is 1 over 2 pi root k over m. So if we know k, we can calculate f, right? But we don't know k at this point. So to obtain k, we use Hooke's law and Newton's second law. The additional force due to the mass of the person is mg. This is equal and opposite to the additional force from the spring. So that means that k times delta x equals mg, right? K times delta x equals mg. Or k is mg over delta x, which when we calculated is 31.85 kilonewton per meter. We now substitute that into the equation for frequency. Frequency is 1 over 2 pi root k over m. Put the numbers in, 0.87 hertz. Yes.
So why do you in one case use the mass of the person and the other case, like you have 1,065, what do you combine on that?
All right. So we know that the force due to gravity is mg, where m is the person's mass, right?
Why not the car?
Because the car has already compressed the springs. We're looking at the additional displacement when the person climbs into the car,
Okay,
right?
okay. So why do you combine that?
And then at the end, we're now saying, what is the vibration frequency of the car mass, the car person system? Right, that's why there's a person sitting on top of the car. All right, another one. An elastic cord vibrates with a frequency of 3 hertz when a mass of 0.6 kilos is hung from it. What will its frequency be if only 0.38 kilos were hung from it? Mass 1, 0.6 kilos. Frequency 1, 3 hertz. Mass 2, 0.38 kilos. Frequency 2, unknown. There we go. There's the situation. So there's 2 possible approaches to solve this problem. We are comparing. In physics, what do we do when we compare things very often? Yeah?
We divide the equation.
Yeah, we divide the equations, exactly. So the formula F equals 1 over 2 pi root k over m can be transformed to k equals m times 2 pi f all squared to determine k, and then substitute k back into the same equation, but using m2 to determine f2, right? But since only the mass is changing, I'm going to use the ratio of f2 over f1 to determine f2. So F equals 1/2 pi root K over M can actually be written as the frequency is proportional to the square root of 1/m, right? Because now the constant of proportionality is 1/2 pi times the square root of K. That's what I pulled out. I do that because people get anxious when they see lots of things here. So I'm doing it by simplifying this equation by putting a is proportional sign in there. So I've got F2 is proportional to the square root of 1/m2, and F1 is proportional to the square root of 1/m1. I put a dividing line between. That is, the ratio of F2 to F1 is equal to that, which is the same as the square root of M1 divided by the square root of M2, or M1 over the square root of M1 over M2. And now multiply across by F1, F2 equals F1 square root of M1 over M2. It's that 3.77 hertz. And you say, how can I know this? Could you grab me, Spence, who can reach up there to get one of those kinetics boxes down? Can you reach that high? No, the next one across. Can you bring me the weights, the black bars that are in there? I need like the equivalent of 2 long ones. So it might be like 4 small ones, or a large one and 2 small ones. Okay, so grab another box. Now put them both out. Get the ones out that you've got. Right? That's what I want. Thank you. 4 of them, good. All right, so watch this. Think about how fast that's moving. Now watch this. I'm going to pull it back the same amount. See?
Wow.
Inertia. Inertia. What does inertia do? Inertia resists changes in motion. Right, exactly. And you can apply that to things like guitar strings as well. If you look at guitar strings, some are thinner than others, right? So if you have a thicker guitar string, it has more mass per unit length than the thin one. It has more inertia, so it's going to move more slowly. Okay. So we can continue to use the analogy which connects uniform circular motion to simple harmonic motion. Are you lost?
Yeah,
You're using your phone.
a little bit, honestly.
You're too tired.
No, I'm a little confused.
Right, could you put your phone away and ask me a question then?
Yeah.
Thank you. Where did you get confused?
There's just so many like new equations, and there's so.
All right, so there's only one new equation, right? And that's this one. Well, there's that, but there's this one as well. All I was doing 2 things. I was showing you how we can describe this backwards and forwards motion. And then I proved to you that we can use the math of circular motion to describe this also,
Yeah.
right? That's all I did.
Okay,
And then I came up with this, and we already defined that, right?
and what, that equation, the one to the right is solving for force,
Frequency,
frequency.
frequency,
Okay,
right? Are you back online with me now?
yeah,
You are. Everyone else back online? So what I was doing, I don't like, and you should not like, people telling you stuff and expecting you just to believe it. This is not a church, right? If you believe stuff, that's fine, but that's not science. Belief is not science. Religion and science do not intersect. Science is based on measuring stuff and then coming up with a mathematical model that helps us predict what might happen in a similar situation. Right? So here we go. We've got our thing back here. We can derive expressions for displacement, velocity, and acceleration as a function of time. Now, what I expect you to be able to do is look up Giancoli and find these expressions. I don't expect you to derive them, right? So we're going to watch the following to see what happens to the displacement versus time. Ready? Watch this. It's quick. So this thing E is following the length of the sine of the angle, right? You see that? Remember, a sine is just the side length for a triangle which has a hypotenuse length of 1. Right? That's all it is.
Could you repeat what you just said there?
Sine,
Like what kind of SI?
NE,
Okay, okay.
sine is just the length of a right triangle, right? The side length of a right triangle, which has a hypotenuse length of 1. SOHCAHTOA, S, opposite on hypotenuse. If hypotenuse is 1, sine is equal to opposite. What?
-1, 0. I
What?
don't know.
I
What are they
get
using?
what
So
time
you've
it
been
is.
using this thing, SOHCAHTOA, with having no idea what it means, right? SOHCAHTOA.
No, I know SOHCAHTOA.
He's
All
not
right,
saying
so
the opposite.
SOHCAHTOA is,
He's not saying it's equal to, it's the opposite side.
Oh.
if this is theta, right? If that's theta,
Yeah,
and we call that the opposite, that's the adjacent, and that's the hypotenuse. What if we said the length of H was equal to 1?
then it's whatever the opposite is.
Sine equals opposite on hypotenuse equals opposite,
Yeah.
all right? And cosine is just the adjacent angle. Right, so all sines and cosines are the lengths of triangles, right? For a given angle, the lengths of triangles with a hypotenuse length of 1. Now, why do they do that? Well, similar triangles have similar ratios, right? So you can use sines and cosines, right, to determine the side length of any triangle.
Going to sleep.
Very simply. Oh, okay. The robot is tired. Has nobody ever told you that in math?
No, I get that, yeah.
They did sign something.
I thought every year should this came
You know what a unit circle is, right?
Yeah, we were
When did you do the unit circle?
beginning of the school year.
Okay, so here is the radius of that unit circle, which is 1,
Yeah,
right?
Okay.
And now we look at this. There's the angle. This over here is sine of theta. This is cosine of theta, right?
yeah,
It's just a side length.
yeah,
That's all it is. So if you wanted to write a relationship between hypotenuse, sine, and cosine, it would just be this squared equals that squared plus that squared, right?
yeah,
If that's equal to 1, what's 1 squared? 1. So 1 equals sine squared theta
That's a good idea.
plus cosine squared theta, right? It's where it comes from.
yeah.
Pythagorean theorem,
We were not.
Yeah, we learned that. It was a good idea.
right?
Yeah.
But you probably just got focused on it being a trig identity and not what it meant,
Yeah, definitely.
right? Not knowing what things mean means you have to memorize them.
Mhm.
If you know what something means, which is what physicists do, how they think, you don't have to memorize anything
Yeah.
because you understand. You say, oh, that's like that,
Mhm.
right? It becomes instinctive.
It's not a math class.
It's not a math class. Exactly. But it's hard to know what that means when somebody tells you at the beginning of the year, right?
Yeah.
So watch this again. Right, can you see how the length of that opposite side is tracking with E?
Yeah.
And that's how you get a sinusoidal wave function. That's what that's called. The shape is sinusoidal. It's both cosine and sine. The only difference between sine and cosine is that cosine starts 90 degrees sooner, right? Okay, so theta is related to the radius A and the displacement in the x-axis. Cosine theta is x over A, right? Here. Cosine theta is x over A.
Yeah.
Can be rewritten as x equals A cosine theta.
Yes.
Further, the rate of change of theta, d theta dt, right, change in angle, is omega, small omega. We've done that, right?
No.
No, okay, so
Omega.
omega. So normally you would see omega written as a capitalized form. The capitalized form is that, right?
Yeah, like yeah.
Yeah, alpha and omega in church,
Yeah.
right? Or ohms
Yeah.
in electricity. And lowercase omega is that.
Yeah.
Yes,
What does lowercase omega represent again?
the angular velocity, how fast something is moving in angle terms per unit time.
So we use that in circular motion, I believe.
Right,
Okay.
I believe we did.
Yeah, I just forgot.
So theta equals omega times the time, right? If theta over time equals omega, then theta equals omega times the time,
Mhm.
right? Radians per second. Do you remember that? I thought we dealt with radians per second, no?
We did, but I just forgot.
Okay.
Yeah,
I don't know if we did.
we definitely did.
All right. So omega, what is omega?
Omega.
Is 2 pi times the frequency, because there are 2 pi radians in a second, right?
Yeah.
In a rotation. So if this is the time, this is the number of cycles per second, what we can do is just write 2 pi here to get 2 pi ft, right? So whenever you see omega, remember it equals 2 pi times the frequency.
It's on the equation.
It's on the equation sheet.
Yeah, so.
Yeah, it
It is on the equation sheet, you got us.
Okay. We substitute into equation 8, we find that x equals a cosine omega t. You need to know this for one of the problems. Yep. Or x equals a times cosine 2 pi ft, or x equals a times cosine 2 pi over the period times t. But it's just a matter of substituting, right?
Yeah,
After one period, the time is equal to the period, and cosine of 2 pi equals 1. And that makes sense since the motion repeats itself. So the velocity is related to, so if you see, time to go, I think, is it 10:45? Or is that early?
it's 10:46.
5 more minutes?
Well, we're supposed to be in 5 minutes. Technology, all
This, I don't know why Siri does that. I
right.
mean, you're supposed to say, hey Siri.
She's always listening.
Yeah. Okay, so the velocity v is related to the maximum velocity as follows. You should look at this diagram and note that v is negative in the diagram. So sine of theta is equal to the negative of v over v max, or can be rewritten v equals v max sine theta. So as before, theta equals omega t. Substitute into equation 10 and replace them with v max. We get v max over a equals k over square root of k over m, or that, or those two. So I'm just showing you how I'm getting velocities, right?
Yeah.
That's all I'm doing.
So this isn't the maximum velocity. This is just the velocity. of-
No, it's written in terms of v max. This is just the velocity of this thing, right? Which is this thing down here.
So
That's
this-
v max. V max is the tangential velocity, which is constant.
I'm talking about like that negative a square root sine.
This
Uh-huh.
is that.
And then earlier in the PowerPoint, we had one with the v equals v max for.
Right,
Just another way to find it. basically.
right. And that's actually one of the things we do, right? To find that they're the same. Look at the math. The top curve is x equals a cosine omega t. The bottom curve is the same, but it's phase shifted 1/4 of a period so that it is a sine function, right? There's cosine. If we move it this way, right, or we move it this way, 1/4 of a period, we end up with a sine function. So we can say the velocity is phase shifted plus 1/4 period with respect to the displacement. Makes sense because at this, when the displacement is 0, the velocity is a maximum, right? When the displacement is maximum, the velocity is 0. So we can find acceleration using Newton's second law, A equals F over m, and Hooke's law. We substitute minus kx for the force, and A for x we obtain, sorry. A max, right? There's A max, it's pointing towards the center. Since the object's in uniform circular motion, the acceleration versus time is directed toward the center. We look at the component of the acceleration in the same direction as v. That's A, right? We got theta there. So A is A max cosine theta, or minus k over m cosine theta. the cosine function, which is phase shifted by plus a quarter period with respect to the velocity. So the acceleration is a maximum at each turning point,
Mhm.
right?
Extreme.
At each extreme.
Where can we find the video in this lecture?
The video, I will post it,
Okay.
okay? All right, is everybody at home? Okay, all set?
Yeah.
Okay, we'll see you later.